So yes, I'd like to talk about science of security, and I'll start with a little background. So around 2008, maybe a bit before then, this idea that we should be doing science we should be doing security more scientifically started to make the rounds, and the chief sponsor of this idea, as I understand it, was the National Security Agency, and since that time it's been picked up by other governments, including the UK government. And the story is basically that we're not doing it scientifically and we should be doing it scientifically, so let's do more science. And once you hear that a few more times, then you start to wonder what people mean. And so I was wondering what that meant. Of course, we were in computer science, and what they say is any field of study that has the word science in it is not a true science. In biology, chemistry, physics, because those are the sciences, right? So we're computer science, so we must be one of these non-pure sciences. I'm trying to convince people that we're a science. So the NSA asked this group called the JSON group to do a report, and a report came out around 2010 saying what we should expect if we were to get a science of security and what the prospects are for that. And a lot of what came back in that report was that we should be doing a lot more formal methods. And we have some very good formal methods available to us. My background, as Shokin said originally, was cryptography, and certainly that's very, very rigorous, very mathematical. And other formal methods are available. However, once I transitioned into industry, I started to wear this other hat of understanding how important system security is. And so now whenever I see there being a lot of push for formal methods, I respect that that's important, but I always want to say make sure we don't exclude the other sides as well, and so I like to see some balance. So I didn't see the balance that I was expecting in this JSON report, and so then I read some more of the other papers that were promoting this science of security. And I got together, this work is joint work with Cormac Hurley from Microsoft, and together we started looking through the literature purporting to do a science of security and encouraging it. And we were a bit disappointed that nowhere did we see any definition of what they really wanted, and there seemed to be these circular exhortations of doing things more scientifically without actually saying what that meant. And so we thought, well, if we're going to encourage people to do this, we should first of all decide what that means, and before we decide what that means, we should figure it out for ourselves, because the last time I studied science, actually I studied it in high school, I guess, and for some reason I took electives in chemistry and physics in first year university, but most of us don't. If we're computer scientists or engineers probably get a little bit more science because they do study some physics and things like that, but computer scientists were not exposed to a lot of science. So across our peers, I think that's probably true as well. So we thought we should, for ourselves, decide what it is that people mean when they say science, and then see whether in our community our security research is being done scientifically. So I'm going to go through a little bit of that. There was a report last year from the National Academy of Sciences in the US, which followed up on this JSON report. There's been several in the US now, of course, but this was on foundational cybersecurity research, and again, they said a lot of the same things, and my question is, what's the underlying motivation for this work? And on the positive side, I think it might be a call for finding a way to improve the quality of the research and its applicability to society to solve real problems, and also a way maybe to justify putting more funding into this area, which I think is a positive. I hope that's what the motivation is, but we're always a little bit suspicious when we see that things are sponsored by the NSA, because they don't have a spotless track record in everything that they've done. So I think it's good that we're skeptical and look into this. So what do we mean by science? Does that, if I say we should do things more scientifically, does that mean we should have more equations, more graphs, more lines on graphs, more numbers, is it repeatable experiments? Is that what we mean when we say science? Or is it that things should be more rigorous? We should have more theorems and more proofs. It's not really clear, because everyone agrees that science is good, but then when we try to define it, it's a little bit difficult. And I guess there's good reason. We don't want to have a tight definition of science because we don't want to exclude any areas or any methodologies or any approaches that might help us. But it's hard to put your finger on exactly what science is, and I think that's doubly true if you're a computer scientist, because I know we over in North America, I don't think you probably get a little bit more science background in Europe. But we don't tend to stress it as much as I think we might. Anyway, Peter Denning has a nice article summarizing this back, I guess about 5 years ago now, about the science in computer science, not specifically about security, but I think if you're interested in a starting place, that's some place to look at. So what this led me to do is to go back and read both books about the philosophy of science, which I'd never read before, and history of science, and I'd strongly encourage that for anyone who's interested. This is really interesting stuff. And I think I was, like a lot of other people, just kind of thought, this is unimportant stuff, I'm not interested in philosophy, but tracking where we came from and looking at the mistakes and how science has been done for a couple of 100 years and what we've learned, I think can help us all. Two books in particular that I found helpful were one by Chalmers, What is this thing called science, and the other one's by Godfrey Smith on Introduction to the Philosophy of Science. And if you don't recognize, let me see, everyone should recognize two faces in that crowd. If you don't recognize more than two faces, who recognizes more than two faces? Who recognizes only two faces or less? No one's going to put their hand up. But if you don't recognize more than two faces, you should read one of these books. You should read one of these books. Should I quiz someone to see if anyone can identify? No. Yeah. Who's the third?
He looks like you.
Einstein and Feynman are there. Okay. Anyway, that's the quiz at the end of. Okay. Thomas Kuhn's in the middle. So, what are the consensus items that we have from other fields of science when we say what is science? And I guess what we really, at the end of the day, I think what we really come away with is there are certain things that we expect when people say that they are doing things scientifically, and it's more principles than tight rules. But one of them is, if theory conflicts with observation, it's the theory that is wrong. The observation helps us correct our theory, and the theory guides us. But when the two come together, it's the observation that helps us correct the theory. Right? And the theory can tell us what can't happen, and if that does happen, then the theory is wrong. So conflict with observation must actually be possible. I'll say a little bit more about this later on. If it's not possible for there to be a conflict with observation, then some people would say it's not science. Science requires induction. I'll say a little bit more about what I mean when I use that word induction, not deduction alone. And claims must be falsifiable. Okay, so I'll talk a little bit more about these things, but these are things which are generally accepted. If you explain to people what you mean by these words, most scientists would agree with these statements. Okay, so let me start with falsifiability. So this is a quote from Popper. A theory which is not refutable by any conceivable event is non-scientific. Irrefutability is not a virtue of a theory, some people often think, but it's a vice. So, for example, if you take some event X, and X cannot be shown to be false by any observation, then that statement X would be consistent with every possible observation you make. That means that you couldn't possibly observe anything that depends on X. And so an observation could not inform you about X at all. And so generally people would say, in that case, that's not a scientific statement because we can't get feedback from the real world in order to tell us whether we're right or wrong. It doesn't mean it's not useful, but it means it's not what we would classically call science. Okay? Because remember, science is about the real world. Okay, so the picture there, if we're observing swans, and we observe a white swan, another white swan, and another white swan, and then our conjecture is that all swans are white. it's possible that we observe a black swan, and that would be something that would contradict our hypothesis, and that would show that we're wrong. But that would be, so the statement X that all swans are white, that would be it would be a hypothesis that could be shown wrong by an observation. Okay? In science, we can never be sure. When we have induction, we look, we observe things, we try to generalize from the specific, try to move from the specific to the general, but we can never be positive that our statements are absolutely true. We can never have the certainty that we would want. Okay, so I use these words induction and deduction, so let me explain a little bit about how I use them. It's like anything else. When we define something, we have to explain our definition so that when I use a word and I'm talking with you, we both understand what we mean. So by induction I mean statements about the real world, and again, we generally want to move from the specific observation to make a general claim, to a general result. By deduction, I typically mean a statement which you can, a deductive statement, you would prove things from axioms and see what the logical implications of those axioms are. So when I talk about the deductive world or the abstract world or the logical implications of axioms, I'm thinking about this is in my mind, and that's the deductive world. Things that come from observation in the real world, I think about that as inductive world. Okay. So for example, we have geometry, we have logic, we have mathematics, things like the Pythagorean theorem, things like Fermat's last theorem, those are in the deductive world. We start with axioms and we see what the logical implications are. When we prove something, we might make an error, but when we fix up the error, when we prove something is true today, it's true tomorrow, it's always true, nothing that we observe is going to show that's false. Okay, that's the deductive world. The inductive world is different. So how could we show that penicillin works? Well, we run experiments, we run trials, we see that people get better. And that's something that comes from the inductive world by running experiments, by running tests. DNA is a twin spiral. That also is something that comes back from the inductive world. We couldn't prove that we could conjecture it, but we could not prove that. Okay? So if we try and summarize then, it's inductive statements that describe things in the real world. Deductive statements do not describe things in the real world. Do we have certainty? We always have uncertainty with inductive statements. It could be that tomorrow penicillin stops working under certain conditions for certain types of agents. With deductive statements, once we've shaken out the bugs and there's no errors in our logic, we have 100% confidence. Okay, so when do we believe or have confidence in an inductive statement? It's when we repeatedly try to show it's false and we scrutinize it, and after long periods of time, no one's shown it's false, many people believe it's true, our confidence increases, but we don't have absolute certainty, but we believe it. And when do we believe in deductive statements? It's when we have a proof. Okay, so that's a little bit of background on how I use the terms inductive and deductive. And so some of you are now saying, hold on a second, so you're saying that mathematics is not science, and people get upset about this, especially mathematicians get upset about this when I say mathematics is not science. Okay, so let's just go through this a little bit. So let's take the Pythagorean theorem. So we take the two sides of the triangle, you take their squares, and they should equal the square of the hypotenuse. If we go out into the real world and we measure a door, and it turns out for this door that I measure, the two sides, and I take the diagonal, and it turns out that a squared does not equal, a squared does not equal b squared plus c squared. Do we say that the theorem is wrong? No, we don't say the theorem wrong. The theorem's correct. The door turns out not to have a right angle. So we thought it was a right angle. We made an assumption it was a right angle. It's not a right angle, so we shouldn't expect. But in that case, the theorem is correct. The observation doesn't show the theorem is wrong. So this is math, because the Pythagorean theorem is in the deductive world. It's not in the real world. So something that's we're thinking a little bit about, in the deductive world, we typically have axioms. And axioms are statements that hold true, we say they're true. They're true today, they're true tomorrow. And then we see what logical implications come from it. In the real world, we typically have assumptions. And so, for example, the axiom could be that parallel lines meet at infinity. We get that from geometry. In security, we'll have an assumption, say the attacker can't take discrete logs in finite fields. Now, we make that assumption. That assumption could turn out to be false. So we have kind of two different types of premises. In the deductive world, our premises are axioms. In the inductive world, we have assumptions. The assumptions can turn out to be false. We can still look at what the logical implications of our assumptions are, and then we can use deduction to figure out the logical implications of our assumptions. And then from those consequences, we can form hypotheses. We can then make observations which can show that our hypotheses are wrong. So the logical implications are incorrect. That then means, if our logic doesn't have any flaws in it, which we'll assume we shake out, that means that the assumptions are wrong. So our observations can show that our assumptions are wrong. So observations that contradict assumptions are possible, and again, with scientific claims, we always have some uncertainty. We might have growing confidence, but there's always some uncertainty. But I think within these definitions, math is not science. Math is an incredibly useful tool to carry out scientific work, but math itself is not science. Okay, so I'm surprised none of you has got up and left yet, because you thought you were coming here to hear about a security talk, and all I've been talking about is induction and deduction and mathematics. So like, well, why am I saying all this stuff to you guys? Like, you should be jumping up and down and saying, you're wasting my time. Okay, so I'll try not to waste your time anymore. Okay, so it turns out, I know that this is shocking, it turns out that not everything has been perfect in the history of security research, and yes, this is a well-known book. Somebody maybe have read. Mistakes were made, but not by me. So this is kind of like, I think maybe what in the backs of their minds, everyone's agreeing that the scientific research in security hasn't been perfect, but of course, you're not the ones that have made the mistakes. Other people are the ones who have been making the mistakes. Okay, so for example, one repeated error that we seem to have is a confusion and a failure to separate this inductive world from the deductive world. And so here's an example of a statement that I find hard to believe we continue to make in our crypto security world. So here's the statement which I take objection to. The statement is, there is no and there cannot be empirical evidence for the security of a design. The only way to do so is to develop a formal mathematical model and language in which to reason about such schemes. And so let me explain why I have difficulty with that statement. If we look at the inductive world, and some of you will recognize this from yesterday's talk as well. If you look at the inductive world and the deductive world, in the deductive world we typically have where our model is. So we have a formal system. And we prove things about our formal system. And that's the individual that made the statement is talking about we can prove things about our formal system. The problem is that we prove things about our formal system and then we imply that those results hold about our real-world system, and there's typically a formal proof, very rigorous, and the formal methodists will impress upon us how rigorous they are, and then they wave their hands and they say, well, yeah, there's some assumptions we made, but all of this stuff holds for the real-world system. But this rigorous proof, and then all of this, these English paragraphs and statements assuming or convincing you that these properties are enjoyed by the real-world system, that's no longer rigorous. So your proof lives in the deductive world, that your proof lives in the deductive world, and the real-world system that you're trying to make the statement about, that it enjoys those same properties, that's something you cannot prove. That's something you have to empirically show, and so we're never going to have confidence about that. So the proofs that we keep being told we have, they don't apply to our real-world systems, and they never possibly can. We cannot prove systems are secure. We can have proofs that certain specific types of attacks might not be possible. But we cannot prove that a system in the real world is secure. That's an empirical claim. We cannot prove empirical claims. Science tells us that. Okay, so for example, we have in the formal system, we have a formal model which says an attack on TLS, it must solve some hard problem. So it must, it would be equivalent to factoring a large number, which we know, which we strongly believe is a hard problem, difficult problem. And yet, then we have side channel attacks. And so, for example, there are timing attacks by which you can recover private RSA keys by taking network measurements, timings, across a LAN, not even touching the physical server on which the key is. And that is what happens in the real world. That doesn't mean that the statement in the formal system is incorrect. It just means it's an incomplete model. There are attacks outside of that model. So again, the actual real world system does not enjoy the properties which you have proven about the formal system. Okay. So the way I summarize this is that the real world's messy details, you can't prove them away. It doesn't matter. You can do whatever proofs you want on paper, but the real world is messier than that. And whether you're trying to do this purely by deduction or magical wands or powders, it's not going to work. You cannot get a proof that holds in the real world because you would have to prove that all of your assumptions are true. And we can't do that deductively. Okay, so another mistake that is sometimes made is that people say, well, our assumptions are reasonable. And the reasonableness of assumptions is not a substitute for carrying out tests and observing. So for example, from Newton we know that the speed of fall in a vacuum is gravity times time. Now this is assuming that air pressure, that we're in a vacuum. In the real world, air pressure is not zero. And so then the question is, well, hold on a second. We still rely on this result from Newton. Well, the reason we rely on it is not because the assumptions are reasonable, because we're not in a vacuum. It's because the result that's stated is useful for making predictions, despite the fact that it's not a vacuum. So reasonableness of the assumptions, it's not rigorous for us to argue deductively that the assumptions are reasonable. We have to carry out, in science, we carry out tests. So here's the example for substitution. I looked on the web for a substitution for butter, and what came up? Mashed avocado. This is not a reasonable substitution. We should not be making reasonable substitutions. We have to carry out actual tests in the real world. We can't just say, well, it's reasonable to assume that mashed avocado is a good substitute for butter. Try it in your baking. See what turns out. See what turns out. Okay. Failure to bring theory into contact with observation. So when we again work purely in the deductive realm and we don't carry out tests, then we don't have a way of self-correcting. So here's an example in our security world. Back in '79, we had Morris and Thompson's paper which said passwords should contain a mix of uppercase, lowercase, and special characters. We went on for about 30 to 35 years, everyone believing this, and we assumed that complex password composition rules would give us better protection in practice. I mean, it makes sense, right? More complex, harder to guess. But under what assumptions, what implicit assumptions are we making in order for that to be the case? So did we actually carry out real A/B tests where you said in a real world situation, not in the lab where we said this is the only way the attacker is guessing. In a real world situation we said here's 50 million passwords and these ones don't have complex passwords. They don't follow complex rules. These ones do. Which one has more compromises over the next year? Did we ever carry out that test? Turns out no one did. Turns out no one did. It's in the reported literature. So the point is we should be looking at what the outcomes are in a real-world experiment not about what logically makes sense. And a related question here is, what observational evidence do we have that changing your password every 90 days reduces exposures? What observation, I mean, these are rules. I mean, it was in U.S. government guidelines for a long time that we should change passwords every periodically. Periods up to 30 days, 60 days, 90 days. Did we have any other, I mean, logically it made sense. I mean, you didn't like the usability aspect. Logically it makes sense. You change your password, it's going to make it harder to do it. Did we have any evidence? Did anyone carry any tests of that? I'll talk more about it later. Unfalsifiable claims. So it's not possible to observe that a real-world system is secure. I mean, I don't. Maybe Ashokan does this. Do you have people? You have your students sit in the lab and look at the laptop to observe? Is this secure? Do we observe? Do we observe security? Is that? It's not possible to observe that something is secure. So it is therefore unfalsifiable to claim that a real-world system is insecure. So if I claim that a real-world system is insecure, for you to show or to prove wrong, you would have to observe a system that is secure. So a claim of a necessary condition for security is unfalsifiable. If I say this laptop is insecure unless you do X, for me to prove that wrong is I would have to not do X and then look at this laptop and say it's secure. But it doesn't matter how long I look at the laptop, I'm not going to be able to prove that it's secure. So it is unfalsifiable. You cannot prove my statement wrong if I say, for that to be secure, you must do X. It's interesting. So what people really mean when they make statements like this is they mean, if you don't do X, this particular attack will probably succeed. And you could show that you didn't do X, and that particular attack is stopped. So that's usually what people really mean when they say, if you don't do X, this will be insecure. But that's not what they say, and we don't define what secure means, so it's not really a tight statement. But we often do rely, and we let people get away with making these types of claims in our security research. And we should be a little bit more careful about that. Okay. Reliance on implicit and unstated assumptions. So there's universal agreement. Nobody will dispute that assumptions should be clearly stated. Okay. Does anyone here think that assumptions should not be clearly stated? Patrick, are you objecting to that? You think? Okay, you'll reserve judgment for later. But everyone will agree. And yet the problem is the field is full of implicit assumptions and full of unstated assumptions. So if we say that complex password composition policies will improve outcomes, and therefore we continue to have these systems where we say change your passwords every 90 days, what are the assumptions under which that will help us? Has anyone ever seen those assumptions written down? I've gone through the literature. I haven't seen them written down. I've seen some brief justifications of, well, this is a motivation for it. We haven't written those down. And so this is another example. I've gone through 4 general statements here of types of errors that we make in security research, which if you try and look at security research and you say, is this scientific or not, they would fail this is how you would do it scientifically, fail that test. Okay. If you don't write down assumptions, it's hard for people to look at them and to try and show them they're false. And so then we again lose the ability to correct ourselves. Okay. All right, so what should we do about this? Should we declare security unscientific? Should we say science doesn't apply to security? Should we fire all the professors that are doing the research and put the grad students in their places? Is that because they could do it better? Okay, what should we do? So Cormac and I looked at this work, and it's easy to pick holes in other people's work. You can pick holes in your own work if you care to as well. So we said, okay, what can we do? How can we try and improve things? So we came up with what we thought were a list of, I think, 10 or 12 principles, and I'll go through those now. And the idea is that maybe this offers us some way to get more on the scientific path or not. It was very curious when we had this main paper was at Oakland last year, and we got like 8 reviews. And it's probably 7 of the most positive reviews I've ever seen in any paper I've submitted. And then there was one review, the person wasn't so happy. And there were a number of objections, and one of the objections was that we made a bunch of statements, some assertions, which I'm going to go through, and they said, well, you didn't prove any of the assertions. And the point is, if we could prove the assertions, it wouldn't be science, because that would be in the deductive world. Anyway, this referee seems to have been overridden by the program chair. Okay, so the first thing we think we should do is clearly define what aspects of science it is that you want. If you push for a science of security and you push for more science, and you rule out nothing, but you don't clarify what it is that you're looking for, you just repeat the word science. This doesn't help anyone. We should be telling people, the sponsors of these programs should be telling people, what are the aspects of science that they find desirable? What do they find missing in the current literature? What do they think if the motivation is that the current research is not helping society in terms of solving real problems, what is it that you would like more of? Because this word science, it's quite clear to me, we don't understand science very well in the computer science community. So be more explicit. I think we need to have a deeper discussion with the people who are convinced that we can prove things and that all we need to do is to prove them, and then the problem's done. That is not recognizing this inductive-deductive split, which people in all other fields of science seem to recognize and to appreciate. We're always going to have uncertainty with scientific statements, so as soon as I hear that someone has proven security, I think that person is not interested in real-world system security, because we do not prove security in the real world. Have you ever proven security of any of the systems you've worked on? No? Modi, have you ever proved any security of the real-world system that you've worked on?
I didn't even attempt.
But you've proven things, right? Right. So you prove things which help us, but you don't make the statement that that actually carries over to the real world system. Okay? And I think we need to have more recognition of that in our community. If there's an absolute guarantee, it lives in the deductive world. It's not in the real world. Okay, so these unfalsifiable claims, they're common in security, and along with these circular arguments, they justify a lot of defensive measures. But if we let people get away with unfalsifiable claims, what's the implication? If you say you must do this in order for this to be secure, I can't prove that wrong, and then tomorrow you say you must do this for that to be secure, and then tomorrow you say you must also do this, we're going to have an accumulation of things. If the things that you must do are unfalsifiable, if I can't show them wrong, I can't reduce this list. So we have to have people be more specific about what they mean when they say you must do something, because they probably mean you could stop this particular attack by doing this. And what they're not saying is there may be alternative ways to stop that also. So does everyone know the True Scotsman story? No, unfalsifiable claim. No true Scotsman puts sugar in their porridge. Are there any Scotsmen here? Are there any Scotsmen? Usually someone puts their hand up and they say, I'm a Scotsman, and I said, you put sugar in your porridge? He said, yes, I put sugar in my porridge. And I just said, oh, you're not a true Scotsman. Are there any true Scotsmen here that put porridge? So this is an unfalsifiable claim. I can manipulate it. I've got enough room to wiggle. I'm never going to show, no one's ever going to show it wrong. Okay, we don't want that. Popper tells us, and a lot of people have trouble with other things Popper has said, and he's sure, but Popper does tell us that falsification is the engine of self-correction. We want to make statements that are falsifiable, because if there isn't an opportunity for people to show us wrong, we're never going to get back on the right track if we're on the wrong track. So that's a scientific, whether you like or hate Popper, that's an interesting scientific principle to have, that we want to have some way of self-correcting, right? Okay, so now this inability to observe security, does that doom us? The fact that I can look at this laptop and I can never observe security, so I can never does that mean we should forget about science when we're trying to do security? No. I think it means we should focus on observable outcomes and be specific about what we mean when we say something secure. We should define that usually, to be useful, that means relative to these specified attacks which I have in mind. My statement says nothing at all about other attacks which I'm probably unaware of. So we should be careful. Excellent paper by J.R. Platt, his strong inference paper, and I think one of the things that he says is, we should design experiments, and when someone comes up with an experiment, we should ask, what hypothesis could this experiment prove to be incorrect, or what experiment could show that your hypothesis is incorrect? And otherwise, what's the purpose of experiments? If, what we do as experiments in security, often we build a system and we do performance testing. Or we build a system and we check whether these 3 attacks will work against this system. Okay, we're basically confirming stuff that we know, but there aren't any hypotheses there. We can't prove that a system is secure, but we can show that we think it's resistant to certain attacks, run the attacks, and they aren't. So that could disprove that hypothesis. But you should always if you think that you're doing science, you should think about what's your hypothesis and in what ways could your hypothesis possibly be disproven? What observation would give you feedback that what you're thinking is incorrect? If there's no observation, then there aren't really any experiments that can put you back on the right path. Okay. We often hear this thing, well, security is special and you don't expect the same out of us as everyone else. We've got this intelligent adversary and that changes everything. And some people kind of seem to want to use this as an escape clause for not doing things scientifically in security, and I think we should just stop allowing that. I mean, the physicists, they don't complain. The astronomers, they don't complain that they can't control the movements of the planets and therefore they don't have to do science. We can't carry out experiments, so we don't have to do things. No, it's an observational science. They look for opportunities and alignments, and when things happen, they can observe. They don't say astronomy is special. We don't have to do science because we can't control our experiments. The people in disease science, they don't say, we've got these adaptive pathogens, and so it's an intelligent adaptive pathogen, and so therefore we don't have to do science. No, they've got their own challenges, the same as we do. Maybe our adversaries have more money, or maybe they're more intelligent, but they have adaptive adversaries in pathogen science as well. They don't look for the escape clause. So we shouldn't let the security is special excuse us from following scientific principles where they help us. Okay. So another one that we've heard read in this some of this literature is that physics should be the role model for all of science, and that's not true. So physics envy is counterproductive, and seeking laws of cybersecurity similar to physics is not necessarily, it's not likely to be helpful for us. So if we want to have a counterexample here, is most biology has little use for the concept of the law of nature, of any law of nature, but that doesn't make it less scientific. So if you look at Darwin, how many theorems did Darwin prove? I mean, he wasn't looking for laws of physics, but very few people will say that Darwin wasn't a scientist, right? So we shouldn't look at one science to be a role model for all the others. And just as a general principle, that's good to keep in the back of your mind. More specifically, one thing we repeatedly see is that crypto should be the role model for a science of security. What we believe is that this crypto envy is counterproductive also. So there's many areas of security, including those involving empirical research, that it's just not, crypto and the rigor is just not a good fit for formal treatments or mathematical role models. Now, that doesn't mean that crypto's not extremely helpful in the cases where it applies, but it's not going to be the answer. And if we try and say that this is the role model for systems security, I'm not sure that that's going to help. If we say that this should be our role model for doing usable security and user studies, I'm not sure that that's a great role model. We do get into this problem again with language, and if in crypto we can very carefully and precisely define things and come up with theorems, we run into problems with language like provable security, and then people are misled into believing that what was proven, in this deductive world actually applies over in the real world. And I think the choice of language here is part of the problem. And if you go through the philosophy of science literature, you'll see that language is always a problem in science, has been a problem for hundreds of years, people using terms that mislead other people, that everyone understands except for everyone else. So this is something that, if we read the literature, we can see happens. The interesting quote from George Box here: all models are wrong, some models are useful. Again, models in the deductive world are extremely helpful to us in focusing our attention, helping us look in certain places for problems, for attacks, but we should recognize that they're always going to be incomplete. Okay, so we should insist on bringing theory into contact with observation. We want to have this deductive world, this world of reasoning, the mathematics, the tools of cryptography. We want to bring that into contact with the real world. We need to have the joining of the empirical work along with the theory. So we need to have both theory and measurement if we want to make success in security. One of the other points here that I think we sometimes miss, and it's a missed opportunity for our research to be more valuable, is failing to insist to put results into full solution context. Often people will be doing research and they'll say they're solving this little piece, and they're not going to worry about all these other pieces. And any individual team or researcher isn't going to solve all the world's problems. But I think there should be an onus on researchers to explain if they're claiming that if they're not making any claims about the results being useful to the real world, then you go to it. If you are claiming that your results are going to be useful to society or useful to the real world, then I think there should be an onus on the researcher to explain how their piece fits into a broader context. Because if we have a whole bunch of little pieces that never have any chance of adding up to full stack solutions, then I think we have a missed opportunity. We should be asking people to do a little bit more planning on working on problems that they think can contribute to full solutions. There's a book I really enjoyed reading and I learned a lot from, 1997, this book by Stokes called Pasteur's Quadrant. And in that book, he takes the test of or the case history of Pasteur, who, rather than pitting theory against practice, he always looked for problems which he could use the theory that he knew and motivated by practical problems, and then develop the theory to solve the problems in the intersection. And the deeper he got into his career, the more he did that and the more practical problems he solved. But he had a deep interest in the theoretical contributions towards making that happen. And often we have, somehow in academic research, the theorists are pitted against the practical people and those trying to solve real problems, the applied, so the theoretical against the applied. And I think that's an incorrect view. We should be looking at where they overlap, because doing one or the other is not going to make nearly as much progress as doing both. Okay, so we should assist that assertions be supported by evidence. I mean, this is I think obvious to anyone doing science, but let's just think about it for a moment. When we conflate unsupported assertions and what I call argument by authority, so I'm the IT guy and I tell you what you must do in order for your system to be secure, and you're not allowed to complain back to me. That's argument by authority. When we conflate unsupported assertions and such argument by authority with evidence-supported statements, then we don't get this corrective feedback, and without the evidence, we can't challenge the evidence. So we need people to state their arguments for why things need to be done. We should, again, insist on explicit claims and assumptions. The challenge here is everyone's going to agree, yeah, we should do it. The question is, how can we actually get this done? And I don't have the answer, but I think it's something we need to look at more carefully. How do we track, tag, list assumptions, and then when you claim that this result holds in the real world, verify those claims, verify those assumptions? And other than saying it's important, and you guys all agreeing it's important, I don't know how we end up with this being in our papers, in our research. And it's this problem of implicit and unstated assumptions goes throughout all of science, and yet I think we have even more than most other fields of science because we have attack models as well as formal models. But I think it's something that requires a little bit more attention. So I'm looking for this forcing function of some way that we can require people to do this. I'm not sure what it is, but this idea that, well, everyone already understands these assumptions, that's not the case. Everyone thinks they understand the assumptions until you really have the deep discussion. Oh, you meant that, I thought you meant that. Yeah, but we didn't state that because that was outside of a model. Well, those are the things we should be writing down. So we should insist on seeking refutation rather than just running tests that confirm that our results hold as expected. So science in general prioritizes efforts at refutation, and if we're doing empirical work and it's always just trying to confirm what we already think, it's like a confirmation bias, then we're falling short of what we can do. Again, to quote Papa here, if we are uncritical, we shall always find what we want. We shall look for and find confirmations, and we shall look away from and not see whatever might be dangerous to our pet theories. The principle here, I guess, of science, to state it maybe a little bit more informally, is we basically want to open up our work to the scrutiny of others. This is why we publish openly, this is why we discuss, this is why we talk, and the idea of opening it up to others is so that they can find any flaws in our arguing, in our data, in how we carried out the experiments, because that's, again, how we self-correct. If we don't have the opportunity to self-correct, then we go down the wrong path and we don't get back on the right. Another really good piece to read if you're interested in this is some work by Tom Longstaff. It's a very short paper. I think it's from an invited talk at ACSAC 8 years ago on barriers to the science in security, and he identifies, I think, some really important points. So I'm been so pessimistic now. You guys are probably ready to quit and to move into. So what are some positive examples in security research? So let me go straight to passwords, where most people have some personal experience. So I think we've made actually a lot of progress here in the last 8-10 years. There was a nice piece of work done by Weir in 2010 where they had access to 32 million leaked passwords, and they went back and they saw, they explored whether this large leaked password set, how that sat in the face of this guidance by NIST, U.S. government advice for U.S. government departments on password security and how complexity and length of passwords translated into security. And what they basically showed was that model has a certain implicit guessing attack, and that's not at all how people in practice guess passwords. In practice, how do people guess passwords? They take a large data set, like 32 million passwords, They ranked them first to last in terms of how often was password 123 used, more than anyone else. What was the next most popular password? What was the next? And then what the attacker does is he just guesses from most frequent to least frequent. So he does a probability-based one. That's not what the model that NIST was using was based on, where we tried to use Shannon entropy and estimate how secure a password was. So they just showed that it was wrong. Shortly thereafter, actually it turned out in 2017, NIST, when they reissued these guidelines, they removed that entire crude entropy model. There was a nice piece of work done the same year at University of North Carolina, Chapel Hill, where the team there got access to the actual passwords used in the university. There was a single sign-on system. And what they showed, and they were looking at this forced password change policy. And what they showed was that if you knew the current password, again, what's the idea of changing passwords? You're worried that someone has access to your password, so you want to force users to change it so they don't have access to the next one. Okay, that's the motivation. So what these guys did was they said they got access to all the current passwords, and this database actually had sequences of users' passwords because you're not allowed to use the last 3 or 5 passwords you've chosen, so these last 3 or 5 are kept in the database also. And they showed that if they had the current password, they could predict the next password, and I think one of the results was that for 17% of real users' passwords, within 5 guesses, they could predict the next password if they knew the current one. Because you take Apple 1 in January and Apple 2 in February and Apple. I mean, we all have these little rules, right? I mean, it turns out everyone else has the same little tricks. Right? So what they showed was that this whole idea, the policy of password expiration, didn't make sense, because if you assume the attacker already has the password and he can predict the next one, as they could, doesn't make sense to force changes. Okay, Joe Bonneau did a lovely study. He got access to a Yahoo data set, real live data set, 70 million user passwords, and explored what the resistance to guessing, what the strength, if you will, password guessing resistance was, and informed a lot of our work. So this was three empirical studies that moved us a long way and led to these revisions. So in the revisions that came out from U.S. government last year, they now explicitly discourage complex password composition policies for the first time. They discourage password changes unless there's a known compromise. They, for the first time, mandate hashing. They mandate salting. They encourage iterated hash. So they basically, I think, looked at the literature that a lot of people have been working on and revised things accordingly. So I take that as a positive influence that we've had on this. So I'll leave it open now to questions if anyone's interested. There's a paper at Oakland last year in a shorter magazine article we had at the beginning of this year, and I thank you for your attention.